Hey students, welcome to the first video lecture of Manufacturing 463 Design of Tooling. So we're going to talk about drawing standards, which are really important. So you're going to be doing a lot of projects this quarter, and in most of those projects you're going to have to do some drawings to go along with them. Remember, when you are doing drawings, the drawing is your contract with the person who is making this, whether that's in your own shop or in another shop outside. That drawing is your contract, and if anything is wrong on the drawing, then the manufacturer is perfectly within their right to make that item to the drawing, and you have to buy it, even if that's not what you intended. And so being able to communicate well on the drawings is really important. And it is part of the precision and the painstaking attention to detail that is necessary for an engineer. So we're going to get started with this. We're going to look at some drawings, and the first thing that we're going to do is we're leading up to the first homework. And that homework is just putting together a simple model in CATIA and then doing the drawing for it. And the reason that I do this exercise just right at the beginning is I want to immediately give you feedback on your drawings. This is a homework. I mean, it counts the same as a homework, but it's not a huge percentage of your grade at all. The grades will typically be pretty harsh on these, but the point is to give you feedback on your drawings. So when you get into the projects, when the drawings matter a lot more, you know what I'm expecting. And so we're going to go over that today to give you the best chance of success, but then we'll also, I'll give you feedback on that first set of drawings. So let's look at the drawing standards. And so the drawing standards are governed by ASME 14.5, which is a standard that has been adopted within the United States. It is similar to ISO standards, but not exactly the same. So some things that you need to do when you are creating an engineering drawing. Every dimension has to have a tolerance, except for max, min, reference, and stock. So it has to have a tolerance. Now, it doesn't have to have a tolerance right where you list the dimension. It can be that that tolerance comes from the title block. When it comes from the title block, we call that a blanket dimension. And so a blanket dimension means that you would put in the title block if the dimension has 1 decimal place, then that's equivalent to this tolerance. If it has 2 decimal places, it's equivalent to this tolerance. Now, one of the things that I see in this class all the time, and a huge downfall that will catch you because CATIA doesn't help you out in this, is that students will just take the default number of decimals and they won't think about it. And so whatever CATIA puts out, whether that be no decimal places or 3 decimal places, they'll just put it everywhere. And that's not the correct way to do a design. You need to think about every dimension. Is this an important dimension? In which case it might get 2 or 3 decimal places. In the US imperial system, generally 2 decimal places. In the metric system, if you're based in millimeters. And if it's something that's not very important, then it might have 1 decimal place. And so you need to make sure that all of your dimensions, if you're relying on that blanket tolerance, they have to match one of the blanket tolerance listings. We'll look at that a little bit more in a minute. And then the other exception to this is for boxed dimensions or basic dimensions, and we'll talk about those in a couple of slides. Okay, so dimensions and tolerances shall fully define features. So you can't leave anything floating. All features must have enough dimensions to be able to position them and give them size. GD&T goes on top of that. That's additional to it, but you have to be able to look at any feature on there and know where it happens. There are a few places where you can assume symmetry and you can assume 90 degrees. if something looks like it's 90 degrees, you can assume it. But with those two options, or anyway, this is true. You have to have dimensions on everything. And if you're not certain, you can put a dimension on it and you won't be wrong. Now, that being said, you can only dimension everything one time. So don't dimension it in the left view and then dimension it again in the front view, because it causes confusion primarily. But if there were a difference between those two, which one is right? And again, if the manufacturer goes through and makes it to either of those two dimensions, they are in the right and you have to pay for it, even if it's not what you intended. So you dimension each feature only one time. Dimensions should be clear, represent the function, and not subject to more than one interpretation. So this is really hard, because often you'll be looking at it and you'll know exactly what you mean to say, but when somebody else looks at it, they may interpret it differently. And so when we get to the title block, you'll notice that in the title block there is a place for checked by and there's a place for approved by. And in this class, I am expecting that when you do a drawing, you are going to have somebody check it. And so you're going to have a classmate look at it and check it. And I am going to try to have some portion of everybody's grade be based on their doing a good job of checking other people's work. So if you check somebody's work and you do a poor job of it, you don't help them to find errors, then that will affect your grade as well. So this is serious, right? Because this is your contract again. And so before you send this out and buy a lot of bad parts, you need to have somebody check it and make sure that they interpret it just the same way that you interpreted it. Drawing does not specify the manufacturing method. So this is a change from older manufacturing processes. It used to be, when I went through school, that you said if you had a tapped hole that had a counterbore on it, you said tap to this size, or no, you say drill to this size, tap with this tap, and then you would say counterbore to this size and then ream the counterbore to this size. Now you don't do that anymore. All you do is call out a hole. If it is a threaded hole, you just call out the threaded hole and the class. And so there's classes of threads, and those give the tolerances on the threads. And if it is a hole where you just need a really good hole, you're not allowed to say drill and ream anymore. What you do is you say what the diameter of the hole is, and if you have a tight tolerance on it, then the manufacturer will understand that it needs to be reamed to get that tolerance. Or if it has a tight cylindricity, or if it has some sort of smoothness on the inside of the bore, some call out for something like that, surface finish or something, then they would understand that it needs to be reamed. But you don't tell them how to do it. The one way that you can tell them is you can tell them not to do something. And so if there is a method that cannot be used for some reason, then you can say may not be cut in this manner. And so some examples of that are if you have a part that is not going to have any finishing processes and is going to be in an oscillating service or a flexural loading, then you might rule out a set of processes like electrodischarge machining, or some of the processes that leave micro cracks in the surface. There are other things. It might be a material incompatibility from the pre-process. So there might be the likelihood of a coolant or some residue that would not be allowable. Like if you're doing something that's going to go into vacuum, you might not be able to have some oils used on your part because it's too hard to clean those oils off before it goes into vacuum. Okay. The dimensions should provide optimum readability. So what this means is choose the best place to dimension something. So you don't dimension to hidden lines ever, unless it's just impossible to see things otherwise. You should not dimension much to section views, because it's unclear if the section view, like if you had it going through the middle of a bolt, it's unclear if it goes exactly through the middle of the bolt or a little bit on one side, and so those things matter to the dimensions that you put in there. So in general, you should dimension things on the view where they make the most sense and leave the least ambiguity. Okay. 90 degrees may be assumed if it's not labeled otherwise. Items are dimensioned for 20 degrees Celsius or 68 Fahrenheit unless you say otherwise. So that means that when they are checked to see if this meets the tolerances, it should be done at 20 degrees Celsius, which is the agreed upon temperature for most items. Dimensions and tolerances are in the free state unless noted or unless it's non-rigid. And so what this means is you can't measure something while it's in the fixture. It has to be out sitting on the table in the free state. Sometimes you'll get something where this matters more than others. When manufacturing a telescope, this matters hugely because the smallest ways of loading something can cause a big change in the way that optics work. And so that's one of the places that this comes from. Tolerances apply to the full depth, length, and width of a feature. Now this one is a little bit ambiguous, but what it means is if we label a position of a hole up on the top surface, that position tolerance is supposed to apply all the way through. But that's a little bit hard to tell exactly what's going on. It's hard to tell where the center of that hole is, and I can guarantee you that if you do not have a call out for GD&T on that hole, when the manufacturer measures it, they are only going to measure it at the top surface, because they don't want to know if the hole is good further down through there, unless you call it out in GD&T. If you call it out in GD&T, then they are going to budget for more metrology time to be able to give you the assurance that the part has met the GD&T that you called out. Coordinate system is right-handed, not super critical to anything that we are doing. So I said that there was one big caveat to the all items must have tolerances, dimensions and tolerances, and one of those is the boxed dimension or the basic dimension. So you can see here that we have a block. It has two holes in it. It has a diameter call out, which applies to both holes. It has a distance between the holes, and it has a true position of the holes with respect to A, B, and C. Now we don't have what A, B, and C datums are on here, but we can assume that it is in sort of the X, Y, and Z directions. So the drawing is incomplete without those. But the problem here can be seen in this dimension, because this dimension tells me where the center of the hole is, and it gives a tolerance on the center of the hole, and that center of the hole can move in both X and Y by plus or minus 0.005 of an inch. However, I also have a true position tolerance up here on the hole, and this says that the center can move by a diameter of 0.003. So this linear dimension says, actually it doesn't say X and Y, it just says X, says that the hole can move 0.005 into the sides. And this true position says, no, it can't move 0.005 to either side. It can actually only move within a circle of diameter 0.003. So it can only move to the sides by 1.5 thousandths, though it can move anywhere within a circle. So in this case, this is over dimension because it is not clear what wins here. Is this the tolerance on the position of these two holes, or is this true position? So what you do in this case is, because I called out true position using GD&T here, then I need to make this distance between the holes be a boxed dimension. That is a basic dimension. This does not have a tolerance. What this says is the distance between these two is ideally 2.5 inches. Now go and find the GD&T call out, which says what the tolerance is on the position of this hole. And so it is a circle that has a radius, a diameter of 3/1000ths of an inch. Okay, let's look at another one. So this is a bolt hole circle. You can see this circle defines there are 8 holes. We see a diameter for the hole. They're 1/2 inch holes, plus or minus 5 thou on the diameter. And then it calls out a true position of 2 thou with respect to A, B, and C. And so the center of each of these holes can move around within a circle of 2/1000ths diameter. And so that hole can move around that much. But when we look down here at the bolt hole circle, the bolt hole circle says that it is 5.5 inches plus or minus 5 thou. And so it has a tolerance. Well, that means that circle can move out by 5/1000ths or in by 5/1000ths. So what positions the center of this circle? Is it this diameter of the bolt hole circle, or is it the true position call out? And so what you need to do in this case is need to give the diameter of this circle as 5.5 inches, and then and in a boxed basic dimension, so a dimension that has a box around it, and it says, okay, this is a perfect circle. This is a datum circle that is 5.5 inches in diameter, and then the center of each one of these holes is a true position and lies in a little tiny circle. Don't have it, but in a little tiny circle around the center that has a diameter of 2/1000ths of an inch. Okay, so somewhere we would also have to have what is the X and Y position of this bolt hole circle. So a really good question is, does that bolt hole circle have a tolerance on its X and Y position, or is it basic? And the answer is, we assume that this circle is perfect. And so the bolt hole circle will not have a position tolerance. It will be at, because it's not a real feature. And it is a datum feature for doing this measurement. And so it will be basic dimensions. If you are dimensioning to the middle of this bolt hole circle from the edges in X and Y, those would also be basic dimensions. Okay, so the final question with this is, do all GD&T therefore have basic dimensions associated with them? And the answer is, what do you think the answer is? The answer is no. Only some of the GD&T callouts have basic dimensions associated with them. If we have cylindricity on a hole, so we're looking at, does the hole line up to a cylinder? Is it bigger or smaller? Is it oval or round? Is it straight along its length? So all of those things are part of the cylindricity callout. We'll talk about that more in the next video, but or in class. Does that have a basic dimension? No, it doesn't have a basic dimension. We still dimension to the position of that hole, and we give the hole a diameter tolerance still, and all of those things have to have tolerances on them, the position of the hole and the diameter of the hole. Now, if you give the position of the hole and give it a true position call out, as well as a cylindricity call out, which is done all the time. If you did that, then there would be a basic dimension for positioning the hole, because the tolerance on that hole's position would be taken up by the true position call out. But the cylindricity call out by itself does not have an associated basic dimension. So that's something that people get confused about. So if you have questions on boxed or basic dimensions, make sure you write them down and bring them to class, or email them to me, because they're really important and they're not totally clear. Often they're something you haven't really dealt with very much, especially when you have to generate your own drawings like you're going to have to do in this class. Okay, last thing for this video is title blocks. So I am providing you with title blocks and drawing templates that I want you to use. They are on the Canvas site for this class, and I need you to use those title blocks. And if you use them, they will get you closer to being correct in your title blocks. But let's look at the things that have to be in the title block. So first of all, one thing is, I don't ever want to see XXXXX in your title block. All that tells me is you did not fill out the title block. So all these places that have X's have to be replaced with something, or they have to be deleted, but most of them have to be replaced with something when you turn it in. Okay, so blanket tolerances are over here in this table. And so what this blanket tolerance means is, if there is a dimension on the drawing called out with two decimal places, then that stands for plus or minus 0.01 inch dimension. So that tolerance gets applied to everything. And then if it has 3 decimal places, this is what you call out. What happens if you have a tolerance that has 1 decimal place? Well, according to this blanket tolerance in the title block, that dimension has to have its own tolerance listed. If you want to, you can add a .x tolerance down here and say what the tolerance would be to cover all of those places, and often that would be a really good idea. But I don't ever want to see a drawing that has, 4.3 inches and 2.1 inches, and then come down here to the table and see that there is not a something that matches it. Also note that these are inch values, and you can tell that right over here in this box. It says dimensions are in inches. If they're in brackets, they're in millimeters. If we have a project where things are in millimeters, then you need to change all these values, because 0.01 millimeters is tiny, and 0.002 millimeters is really tiny. So there are certainly machines, I worked with machines that can hit those kinds of tolerances, but does that apply to the current situation? Typically not. And you wouldn't ever also have something that is 0.003 millimeters per inch. So you would have to change all these values in the table to make sense. Note that size and scale are of the drawing, not of the part. And so is the drawing an A size or a B size or a C size? Is the scale of the drawing 1:1 or 2:1 or 3:1? And so these need to be filled in. You must have a date and a revision number. Even if it is revision 1 or revision A, it doesn't matter what you use as the way that you're going to mark that. But I need to know that you know have some control of your revisions that are going through this drawing. And it will actually help you, because you're going to start out with revision A, and then your friend is going to look at it and give you a whole lot of changes, and it would be a good idea to update it to revision B or revision 2 after that. So if you happen to have one printed or you're making a PDF, you know that it is the right one. So you must have the date and the revision. So this is the date that that revision happened. Okay, you should have your name or whoever's name of whoever drew it, the date that they drew it. You should have somebody who checks it and the date that they checked it, and then somebody approved it and the date that they approved it. Now, whoever approves it is probably going to be you in this case. On the group projects, it may just be somebody else in the group, doesn't really matter. But all of these people, the person who checked it and the person who approves it, are saying, we have checked this and we are putting our names on this drawing saying that it is right. And that makes, in industry, you be liable if there are errors on that drawing and you end up being told by the manufacturer that you have to buy several $1 million of components that are not made correctly because your drawing was wrong. You are going to be held liable. So this check is serious. But you must have one person check it. If you want to have 2 or 3 people check it, that's fine. That's great. One thing that I would say is don't just be putting names down there, though. And don't be filling in people's names when they're not actually checking it either. Okay. Weight of the part is optional. It is helpful to have. Because it sort of it lets somebody know what the size is. So a lot of times you look at a part on this drawing and it's hard to tell if it's 1 inch across or 100 inches across or 100 millimeters across. And one way that you can tell that is, hey, this thing weighs 1 pound. Okay, well, 1 pound is kind of going to be a handful of part. If it weighs 1 ounce, then it's kind of going to be, you know, something you can pinch between 2 fingers. And that sort of gives you a scale. You must have the material that it's made out of. For finish, you can have machined or ground, just depending on whatever you think. For everything that you do in this class, I want a real project name in here. So I don't want to see Manufacturing 463 project. You could have project 1, or you could have gauge project. That would be fine. Title, I want to know what the name of the part is, so you should put the name of the part in here. And then drawing number, you're just going to have to make something up, but I want to see something. And then sheet 1 of 10 or 1 of 1, something like that, just so we know how many drawings to be looking for. So your first homework, you're going to find the assignment for this on the Canvas site. But what we're going to be doing is you're going to be making a part. The dimensions are all millimeters for this part. So remember, you can go into options and then to parameters in general, and you can change the units in there. If you have a question about that, email me and we'll make sure you get the units changed. You're making a 2-view drawing of the part, so you need at least a top view and a side view. You must use the B-size drawing template that is on the Canvas site, and you want to make the scale of this so that it fills that page pretty well with the 2 views. You don't want a little tiny view in a great big sea of paper, or you wasted a lot of paper. You also can't have the views so big that you can't fit the dimensions around them. You need every dimension to be the correct number of decimal places. So notice on here, there are no decimal places on everything. So you're going to have to use engineering intuition to figure out what those decimal places make sense. If you have something like this outer diameter, so this outer diameter is 90 millimeters, would that really matter? Probably not very much. It's not fitting into anything. Down here in the GD&T section, I say that the diameter of this shaft has to fit into something. Also, you have this hole in the middle, and there's probably something, an axle that fits in that hole. So those are going to have really tight tolerances, so they need to have quite a few decimal places. The thickness of this back part at 20 millimeters, is that really important? Probably not super important, so it wouldn't have very many decimal places. I'm leaving it to you to figure this out. You need to label the datums. Notice there is A is the bottom surface, B is the center line of the bore, and C is this face right here that the arrow is pointing to. Remember that you have to dimension from datums when you are dimensioning. So I will tell you right now that one thing that people often get wrong on this is that they will put this center line, because of the way that this is done from a center line, they will put a center line and say that this face is 15 millimeters away and this face is 15 millimeters away. The problem with that is that those are not dimensioning from the datum. The datum is this side face over here. So you should have it say 15 millimeters from this side face to the center line. And that's important because that sets it with respect to this secondary axis here in our axis system. But then to dimension from this face to the face that's over here on the other side needs to be a 30 millimeter dimension. And on both of those, you're going to need to figure out how important they are and figure out the correct number of decimal places for them. Okay, define GD&T if the center shaft, that is this part that is 40 millimeters in diameter, needs to fit in a hole. So I want you to think about what that is. And I will tell you right now that true position alone is not sufficient for something to fit in a hole. True position would get it to the right place. On this part, that would get it, it would get it set to the right location around this axis, primary axis that we have, so that things would be concentric. But that's not sufficient for something to go in a hole. You have to go beyond that, add more GD&T to this shaft for it to be able to go into a hole. So I'll leave you to think about that, but what else is important? And then the three mounting holes need to have bolts that will attach to another device. These through holes are not threaded. And so there needs to be something about these holes. You're going to give them GD&T also. Notice on both of these, you're going to have basic dimensions, which you're going to have to be really careful about putting basic dimensions in the right places. And again, for these holes to line up with other holes, it is insufficient to only have a true position. And so you will have to have true position and think about what else matters for a bolt to go through that and hit another hole. And then you're going to need to fill in the title block fully. All right, so this assignment is on the Canvas site along with the due date, and that's also where the drawing templates are. So with that, we're going to conclude video 2A, and I will see you back here for video 2B in a little bit.